structuring the second event risk, subcontractors going out of business. Now, let us insert the risk of subcontractors going out of business. Remember that there's a list of 10 subcontractors where each one of them has the same probability P of going out of business at 5%. If you think it over, you could also structure this problem in the same way we did it for the previous case. Define 10 lines, one for each one of the 10 subcontractors, and multiply the probability of 5% with a Bernoulli distribution times the individual severity of each one of them going out of business, which has been defined with a PERT distribution with the most likely value of $4,000, a minimum of $1,000, and a maximum of $10,000. This would create 10 lines each, one of them, containing a formula such as this one, equals risk Bernoulli, open parenthesis P, close parenthesis, times risk PERT, open parenthesis, minimum, comma, most likely, comma, maximum, close parenthesis. Now, you could add up all those 10 formulas into a sum function cell, and there you would have your total risk defined for any number of subcontractors going out of business. This is a relatively good solution since each one of the eventual severities of individual bankruptcies is generated independently from one another. In other words, we are not assuming at any given iteration with 2 or more bankruptcies that each bankruptcy for those 2 or more subcontractors occurs at the same severity level. There is another way of dealing with this type of risk by using the binomial distribution as follows. 37. On cell K17, invoke the define distribution icon in order to retrieve the palette window. Over the common or discrete tab, select the binomial. 38. Click on the Assign Excel References as Arguments button in order to retrieve the 2 respective parameters required for a binomial, n and p. 39. Make a reference to C17 for n equal 10 subcontractors and C17 equals 5% probability of bankruptcy each. And then click on the upper right-hand corner icon of this small window to return to your distribution definition chart. At this point, the chart should look like this. At this point, this function counts the number of subcontractors that probabilistically would go out of business. By shifting the vertical delimiters between the number bars, you will be able to interpret different probable results. 40. For example, drag your first vertical delimiter between the 0 and the 1. And the second delimiter between the 1 and the 2. There is close to a 60% probability that no subcontractor, 0, will go out of business, given the fact that there's 10 on the list and that the individual probability of each one of them going bankrupt is of 5%. Also, there is close to 32% probability that exactly one subcontractor will go out of business, given the fact that there is 10 on the list and that the individual probability of each one of them going bankrupt is of 5%. There is only close to a 9% probability that either 2, 3, or more subcontractors will go out of business, given the fact that there is 10 on the list and that the individual probability of each one of them going bankrupt is of 5%. It can be demonstrated that this binomial distribution with n equal 10 and p 5% works exactly like 10 Bernoulli distributions added together, counting the number of bankruptcies. Now, let us incorporate the severity part of this type of risk. On the previous exercise, we had multiplied the frequency part of the equation generating ones and zeros with a Bernoulli times the severity part of the equation containing a PERT distribution. Following the same logic, you could create a function such as the following on cell K17. Equals risk binomial, open parenthesis, C17, comma, B17, close parenthesis, times risk PERT, open parenthesis, G17, comma, F17, comma, H17, close parenthesis. We have seen so far that by adding a binomial distribution replacing 10 individual Bernoulli distributions, we can improve the efficiency of the model by reducing its size and improving its simplicity. However, this previous equation generates a subtle problem on its severity part, the PERT distribution. If at any iteration you generate a scenario where 2 or more bankruptcies are occurring, and this event happens on approximately 9% of the iterations generated, this simple multiplication is assuming that by its PERT severity function, all of those bankruptcies impact with the same severity. For example, if on any given iteration the binomial distribution generated 2 events and the PERT distribution generated, say for example, a severity of $8,000, then the total amount for this risk would be multiplied to obtain a risk for $16,000. 2 times $8,000. This could be construed as a simplification since hardly both events will occur at exactly the same magnitude of damage or severity. In other words, what we want to do during the simulation is to generate random numbers for any given possible events being driven by the frequency counting distribution. In this case, the binomial one. The way to solve for this type of situation is through a convolution, not a simple raw multiplication. At every single iteration level, not only does the number of bankruptcies change, but also every single severity for each bankruptcy changes. It is not that the severity level of that bankruptcy remains equal for every single iterated number of possible bankruptcies. Maintaining the same bankruptcy severity for all of them at the iteration level is equivalent to the previous equation on which we simply multiply frequency times severity. Convolution is something else. It goes beyond multiplication. It is not simply multiplying number of bankruptcies times a fixed severity. It goes by adding individually generated bankruptcies by the binomial distribution of different severities at each iteration level. Convolution is implemented on at risk with the compound function.